At first glance, the universe looks chaotic: supernovas exploding, galaxies colliding, black holes consuming matter. Yet when researchers analyzed new high-resolution data in 2025, what they found was the opposite: an extraordinary balance that seems almost too exact to ignore. We'll look at fresh Webb observations and recent quantum results that sharpen this puzzle, showing how the cosmos might be far less random than it appears. Conditions for life are not just rare, they seem almost unattainable without precise tuning of physical laws. So is our universe finally adjusted by design, or shaped by something we don't yet understand? And when we look closer at that chaos, the picture becomes even stranger. The illusion of chaos versus hidden order. When most people imagine the universe, the picture is one of upheaval. Stars swell until they detonate, scattering matter in every direction. Galaxies collide with such force that their spiral arms warp and tear. Black holes consume anything that drifts too close, leaving regions of space that not even light can escape. To the casual observer, it feels as if destruction dominates, as though the universe is ruled by violence without underlying purpose. The more astronomers peer into space, the more of these catastrophic sights they uncover. Taken at face value, it gives the impression of a cosmos driven only by chance and ruin. Yet as data accumulated and new instruments sharpened our view in 2025, another possibility began to emerge. Beneath that apparent chaos lies a structure that obeys subtle but unrelenting rules. Over decades, researchers pieced together maps of the cosmos, from broad surveys of galaxies to measurements of faint radiation left over from the beginning. In the past, those pictures were patchy, offering hints rather than clarity. But the James Webb Space Telescope changed the conversation by revealing unexpected details earlier than anyone anticipated. Webb identified astonishingly mature galaxies appearing within the first few 100 million years after the Big Bang, far sooner than models predicted. Alongside them appeared a population of compact red sources, objects that may represent unusually early black holes or dense stellar clusters. These findings unsettled assumptions about how structures develop, suggesting that the universe has a more organized timeline than disorder alone would allow. Patterns, not randomness, stand out once the faintest light is resolved. This clarity also alters how we interpret explosions and collisions. A single supernova, for instance, looks catastrophic, a star blasting itself apart in one final act. Yet the elements forged in its core, carbon, oxygen, iron, are scattered across space in the process. Without that cycle, planets like ours could never exist. A galaxy collision may appear as violent destruction, but it compresses clouds of gas that trigger a new generation of stars. From a narrow perspective, these events look like chaos. From a broader one, they appear necessary steps in a system that builds complexity over time. Condensed into one simple idea, destruction in the universe often produces the raw materials for creation. Evidence supporting this deeper order grows stronger when we examine conditions in the early cosmos. Measurements of the cosmic microwave background show that density ripples, the initial seeds for structure, were staggeringly small, fluctuations of only 1 part in 100,000. That number, roughly 10^5, proved crucial. If the ripples were much smaller, galaxies could never have formed. If much larger, gravity would have pulled matter together too quickly, collapsing the system before stable worlds had a chance to develop. The fact that those irregularities landed within such a narrow band offers one of the clearest indicators of why galaxies, stars, and life became possible. Attention then turns to the forces governing matter itself. Gravity binds the large-scale universe, electromagnetism shapes atoms, and the strong and weak nuclear forces determine how elements form and change. Each of these operates within a precise range. In 2025, refinements in both Webb's observations and theoretical studies suggested that the margin for life-supporting values may be even slimmer in certain areas than older models implied. But it would be inaccurate to say all tolerances constantly shrink in the same way. Instead, some analyses highlight smaller windows than before, while others remain debated. What emerges is not a uniform narrowing, but a picture that demands careful re-examination of how fine the balance truly is. This shift changes perception. The explosions and enormous collisions that once looked like aimless accidents begin to appear as controlled mechanisms. A black hole consuming matter may sound like ultimate annihilation, yet its gravitational grip shapes galaxies into ordered spirals. Energy carried outward by dying stars fertilizes new neighborhoods for creation. Rather than unchecked destruction, the system redistributes matter and energy according to limits that preserve coherence. The more scientists identify those limits, the more the surface spectacle of violence transforms into an underlying framework that has held for billions of years. The implication raises unsettling questions. If the doorway to stability is that narrow, what does that say about the nature of the universe itself? Life does not arise from one condition alone, but requires a web of factors to align all at once: temperatures of stars, atomic stability, planetary chemistry, distances between galaxies. A small deviation in any, and the possibility for life as we know it collapses. The very fact that we are present to examine these conditions implies that the universe has carried its balance through countless transformations that could easily have tipped the other way. By interpreting data in this light, researchers focus less on the randomness of catastrophic events and more on the persistent structure they reveal. Spectra from supernovae now show energy dispersal with remarkable consistency, tied back to constants established at the foundation of physics. Galaxy mergers, though dramatic, create predictable bursts of star formation that follow gravitational models to exacting degrees. What first seemed arbitrary now points toward laws that restrict outcomes into patterns, turning apparent chaos into choreography that continually builds complexity rather than erasing it. The contrast between illusion and hidden order impacts not only how scientists build models, but also how we understand our position within this universe. Every observation of light from distant stars becomes a confirmation that conditions remain stable long enough for such complexity to emerge. The timeline from the Big Bang to our existence resembles not uncontrolled disorder, but a sequence of stages operating within sharply defined constraints. With Webb's sharper vision and high-precision measurements, this picture of balance has only grown harder to dismiss. At the close of this inquiry, one puzzle rises above the rest. Could all of this order, so dependent on delicate ranges, be the result of necessity, chance, or something altogether outside those categories? The truth so far is that life occupies a reality where the leeway for survival seems astonishingly tight. We are left looking out at skies filled with explosions that paradoxically testify to enduring stability. The supposed chaos turns out to have been a mask for precision. Coming up, one concrete number that makes this fine-tuning problem feel unavoidably real, and a Webb surprise that pushed cosmologists to rewrite their assumptions. And that brings us to the fragility of the very settings that govern existence, where the question becomes not what patterns we see, but whether the numbers themselves could have settled any other way. The fragile settings of physical constants. When the conversation turns from cosmic structures to the conditions that make them possible, it quickly narrows to a few immovable numbers. These are not measurements we assign by choice. They are physical constants that govern everything from the formation of atoms to the lifespans of stars. Our existence depends on them, and many appear to occupy ranges so narrow that even tiny deviations would prevent life-supporting chemistry from emerging. What scientists debate is not whether they matter, but how tightly their values are constrained, and whether any alternative combinations could have worked at all. Updated calculations in 2025 suggest that in several key cases, the tolerances are narrower than once assumed, though researchers continue to argue about the exact limits. Take gravity. For everyday life, it means objects fall and planets orbit their stars. But for physicists, it is defined by a coupling constant so small it is dwarfed by other forces. If gravity were appreciably weaker, stellar formation could never have begun. Clouds of hydrogen would drift apart before collapse. If it were stronger by a comparable factor, stars would grow unstable, burning through fuel so quickly that planetary systems could never support biology. The interval where stars remain both stable and long-lived is quite restricted, and the night sky filled with luminous suns is evidence that this value happens to rest inside it. Another example lies inside the cores of atoms. Neutrons are slightly more massive than protons, a difference that at first seems trivial. Yet that detail sets the stability of nuclei across the periodic table. Were the ratio different by only a small amount, hydrogen, the simplest and most abundant element, could never have endured beyond the Big Bang. Shifted in the opposite direction, and stars would struggle to synthesize carbon or oxygen, cutting away the building blocks of cells before they could form. Physicists explore this sensitivity using nuclear and stellar models. One well-known case is the Hoyle state in carbon, a delicate resonance in atomic nuclei that allows stars to produce both carbon and oxygen efficiently. Adjust the strength of the nuclear force by only a few percent, and that resonance disappears, halting the cycle that makes organic chemistry possible. Here, the interplay between microscopic constants and macroscopic environments becomes impossible to dismiss. Electromagnetism reveals an equally fragile stage. Its strength determines how electrons orbit and how atoms bond. Alter the coupling constant upward and electrons cling so tightly to nuclei that chemistry stalls. Lower it, and atoms fail to hold electrons altogether, leaving no foundation for molecules. Only within a narrow middle band can atoms link into complex partnerships that construct proteins, DNA, and cell membranes. The world of molecules that surrounds us is not guaranteed. It exists only within the permitted interval of this single interaction. These cases illustrate a broad theme. Many constants outline slim corridors where conditions remain suitable for life. But the degree of precision varies, and not all claims of impossible odds hold up the same way. Some tolerances are established with confidence, while others remain subject to debate. Updated analyses in 2025, combining particle physics, astrophysical data, and improved simulations, tightened constraints in several areas, yet scholars caution that uncertainties remain, especially where multiple processes overlap. The broad conclusion is that small changes can drastically reshape stellar nucleosynthesis and planetary chemistry, even if the exact margins are still under examination. Among the most dramatic examples is the cosmological constant, the parameter that dictates the accelerated expansion of the universe. In natural Planck units, this constant measures about 10^122. Any increase of significant size would have driven matter apart too quickly, preventing galaxies from condensing. Any decrease could have reversed expansion before structure took hold. Galaxies, including the one that hosts our Sun, could form only because this term sits unimaginably close to zero, yet remains slightly positive. It is one of the starkest known illustrations of apparent fine-tuning. Physicists often compare these constants to the dials of a machine. Each one must be positioned correctly, not just in isolation, but in combination with all the others. What sharpens the picture is that these dials were fixed from the very beginning. There was no opportunity for nature to recalibrate after the Big Bang. The system either launched with the right configuration, or no enduring complexity would ever arise. Probability estimates attempting to evaluate this setup tend to show that life-permitting universes are a small fraction of possible outcomes, though the reliability of those statistics is itself debated. Whether coincidence or necessity, the values appear unusually well placed. Some readers may object that constants simply are what they are, and that speculating about other values misses the point. But the persistence of narrow ranges, underscored by fresh calculations, makes the question unavoidable. If minor shifts in nuclear parameters can extinguish carbon production, or if a cosmological term of 10122 is required for galaxies to form, then the existence of stars, planets, and observers cannot be separated from these exact conditions. The improbability may be overstated in some popular accounts, but the pattern itself is difficult to ignore. What emerges is not a story of inevitability, but of precarious conditions narrowly met. Life rests upon constants that act as gatekeepers: gravity to regulate stars, nuclear forces to balance atoms, electromagnetism to permit chemistry, and dark energy density to allow galaxies at all. Together, they form a set of interlocking locks that opened only once in just the right way. Recognizing this fragility has consequences. It shifts attention from the visible drama of explosions and collisions to the invisible frame of numbers that make those events constructive rather than destructive. It also raises the deeper puzzle of whether these constants are intrinsic features of reality, products of chance within a larger ensemble, or signs of principles not yet uncovered. Whichever stance one takes, the conclusion remains that their settings shaped every stage of cosmic history. And to see just how much depended on those balances, we need only step back to the beginning. After the first instant, matter and radiation rushed outward in an almost uniform fog. From that state, galaxies and stars had to emerge against incredible odds. How such intricate forms could grow from such smooth beginnings becomes the next central question. Galaxies, stars, and the impossible formation story. After the first instance of expansion, the cosmos had no galaxies, no stars, no planets, only a hot fog of particles and light spreading outward. The story of how that smooth state became today's universe of structures is the story of galaxies, stars, and the improbable path that linked them. For matter to clump at all, density fluctuations had to be present from the very start. Measurements from WMAP and Planck satellites revealed these ripples in the cosmic microwave background, and they measured just 1 part in 100,000. That tiny ratio, 10:5, was enough to serve as gravitational seeds for later formation. If the early field had been smoother, no condensation would have occurred. Too rough, and collapse would have produced an unstable mess. The success of those numbers is why galaxies could ever appear. From those faint beginnings, gravity began to draw gas into filaments, nodes, and eventually the first stars. The cosmic microwave background makes clear that the seeds were small, and growth should have been gradual. Yet in 2025, the James Webb Space Telescope revealed something astonishing. Some of the earliest galaxies, visible less than 1 billion years after the Big Bang, already looked mature. Many showed organized shapes such as disks rather than loose, irregular clusters. The puzzle is obvious. If small ripples only permitted slow accumulation, why did Webb see massive systems so quickly? The answer cannot be a simple dismissal of models, but it does require revision. The small CMB ripples defined a careful framework for structure growth, while Webb's 2025 observations challenged standard timelines by revealing galaxies assembled faster than expected in certain regions. For theorists, this dual picture opened an urgent question. Both slow and fast processes were somehow written into the same early conditions. The framework for that growth included unseen participants. Dark matter, although invisible to light, provided the gravitational scaffolding through which normal matter could collapse. In simulations, it is dark matter halos that form the scaffolding webs, guiding gas to collect and ignite as stars. Adjust the abundance, and the results change drastically. Too little and normal matter never coalesces, dispersing into a thin mist forever. Too much and dense traps form, collapsing prematurely into black holes and overwhelming clusters. Models of galaxy evolution show that only within a narrow range can structures resembling today's galaxies occur. Alongside this sits dark energy, a different ingredient shaping the cosmic background. Its effect is to accelerate the expansion of space. If this term had been much stronger, matter would have flown apart before galaxies could stabilize. If much weaker, gravity would have reversed expansion too quickly. The balance between dark matter and dark energy, as defined in lambda models, controls how galaxies arise at all. Simulations repeatedly show how sensitive these outcomes are to those two magnitudes together. Into this arrangement step the galaxies themselves, dynamic engines of star production. Stars formed from collapsing gas clouds within halos, lighting up and beginning nuclear fusion. Many of the first massive stars lived only briefly, exploding in supernovae that enriched their surroundings with heavier elements. This chain produced the periodic table as we know it. But stars require stability across millions or billions of years to act as light sources for planets. The ratios established in the early universe determined whether such stability would exist. What looks like inevitability is instead an outcome rooted in narrow limits. The evidence accumulated since Webb's 2025 data has deepened the challenge. Instead of late-blooming galaxies, astronomers must now account for massive collections of stars already present when the cosmos was very young. They possessed internal structures once thought to demand longer timescales, organized disks, scattering of heavy elements, sometimes even hints of spiral features. The implication is not that physics failed, but that hidden efficiencies in structure formation must exist, perhaps linked to how dark matter gathered in the first halos. Researchers continue to test competing explanations, but all agree the pace of early assembly is faster than models allowed before Webb. This entire arc, CMB ripples of 10.5, the growth of nodes in the cosmic web, gravitational scaffolding of dark matter, balancing influence of dark energy, and Webb's discovery of early mature galaxies, converges on one message: structure is less forgiving than it looks. Without the correct size of density seeds, there would be no galaxies at all. Without the right blend of matter and expansion, there would be no stars to populate them. Without long-lived stars, no planets. And without planets, there would be no possibility of observers to notice any of it. The boundaries are narrow at every stage. The sensitivity of this construction often disappears when we look at the night sky. A spiral galaxy bright in our telescopes looks permanent, inevitable. Yet each spiral arm traces itself back to numbers defined at the edge of measurement accuracy. The gas in those arms is held in shape not by chance, but by constants and dark components tuned inside fine margins. Consider again the Webb discovery of galaxies assembled earlier than imagined. Their existence does not erase the delicate structure seen in the microwave background. It shows how both delicacy and speed must be reconciled in a single framework. For scientists, the question has shifted from whether conditions were fine-tuned to how so many different requirements lined up at once. Every star that burns, every planet around those stars, depends on that improbable chain. The vastness of space hides the fact that the window for such outcomes is small. Too different a density field and the sky would be empty. Too different a balance of dark matter or dark energy, and galaxies would never stabilize. A great deal of chance or some guiding necessity set the dials in one precise range. We cannot change them retroactively. We can only notice that they hold, and that without them, there is no story to tell. One way to grasp the enormity is to realize that the visible cosmos, everything from the faintest star cluster to the largest spiral galaxy, represents confirmation that multiple independent conditions landed correctly. That realization leaves us with an unsettling thought. How did those perfect seeds and invisible scaffolding line up so precisely? So far, the evidence shows razor-edge values at nearly every turn. Yet explanation is still open. Is this careful balance the outcome of natural selection across universes, the work of many worlds' probability, or something not yet on the scientific horizon? The next stage of inquiry takes us from galaxies and stars to worlds much closer to our experience, where planetary systems multiply in number but rarely in similarity. Exoplanets and the expanding evidence. In recent years, the search for other worlds has moved from speculation to precision science. By 2025, exoplanets were no longer rare surprises. They crowded the catalogs by the thousands. What changed was the level of detail. Webb and other observatories advanced spectroscopic studies that year, allowing teams to detect gases such as water vapor and carbon dioxide in several exoplanet atmospheres, and even directly image young giant planets, including those in the HR 8799 system. These steps took the field from tallying planets to investigating whether any could resemble Earth in the conditions they host. The early focus rested on the habitable zone, the orbital band around a star where liquid water could, in principle, remain stable. For decades, this was more an exercise in theory than in measurement. Now instruments could confirm not just orbital distances and sizes, but also atmospheric traces suggesting whether those orbits might sustain surface water. The result was a filtering process. A planet might occupy the right orbital range, but without an atmosphere to stabilize pressure, or without shielding against stellar winds, liquid water would remain impossible. This distinction sharpened as the catalog expanded. On one side, surveys revealed dizzying variety, hot Jupiters brushing the edges of their stars, mini-Neptunes orbiting in tight chains, or rocky planets scattered far from habitable zones. Planetary systems assembled in nearly every arrangement models could generate, making planets themselves look inevitable wherever stars form. On the other side, stability suitable for biology looked scarce. Data showed that while planets are common, factors required for long-term surface habitability, moderate temperatures, a magnetosphere, stable atmospheres, low stellar activity, remain difficult to satisfy together. Early atmospheric probes helped narrow candidates, but most revealed hostile climates or destructive stellar environments. The 2025 Webb results widened this contrast. For the first time, subtle details became clear in specific atmospheres. One spectrum showed water vapor enveloping a distant world. Another revealed the fingerprint of carbon dioxide. Molecules containing carbon stirred interest because on Earth they support complex chemistry. But researchers emphasized that these were not direct signs of life, only markers of chemical environments. In several young gas giants, Webb traced abundant gases but conditions incompatible with biology. Still, being able to capture these signals set the framework for analyzing smaller Earth-sized worlds orbiting nearby stars. Nearby red dwarfs provided the earliest chances, given their prevalence and the compact orbits of planets around them. A handful of rocky planets in these systems appeared to carry water vapor in their skies. For a moment, this looked promising. The distances placed them in their stars' habitable zones, and spectral lines crossed out certain barren scenarios. Yet the same red dwarfs posed severe challenges. Their frequent, violent flares threatened to peel away atmospheres or irradiate surfaces. Atmospheric models suggested that stability could exist only with stronger than expected magnetic defenses. The question became not whether liquid water was possible in a laboratory sense, but whether it could survive long enough in a real system to support biology. This pattern repeated. For every world that initially seemed encouraging, deeper study revealed hazards. Some planets possessed the right temperatures but no atmosphere capable of maintaining water. Others carried gases typical of dynamic chemistry but orbited stars too violent for long-term stability. What looked generous at first, the sheer variety of planets, reduced dramatically once life-friendly requirements were stacked together. No single criterion was enough. Each needed company from several others. Understanding this made Earth seem less ordinary. Here, liquid water is stable across geological timescales. The planet's magnetic field provides protection from solar wind. The atmosphere supplies greenhouse regulation without slipping into extremes, supporting cycles of carbon and oxygen. Most crucially, these features occur together. Each property is seen separately elsewhere, but rarely in combination. In 2025, as data from Webb and ground-based surveys confirmed how seldom multiple favorable factors overlap. Our planet's circumstances stood out with sharper contrast. The abundance of exoplanets did not dilute Earth's uniqueness. Instead, it highlighted its rarity. The refining of atmospheric studies underscored this rarity. Spectrographs now captured whispers of molecules across light years, but each positive sign of water or carbon demanded strict interpretation. Scientists avoided declaring signals as biosignatures. Instead, they emphasized how such molecules shaped planetary climate and chemistry. Reports that year noted water vapor around sub-Neptunes and CO2 absorption in gas giants, but none claimed life detection. Even these results were striking, proving for the first time that modern telescopes could detect atmospheric signatures at interstellar distances. They demonstrated possibility, not confirmation. In this light, the search became less about finding another Earth and more about understanding the full distribution of planetary outcomes. Some stars produce chains of rocky planets without atmospheres. Others wield giant planets that destabilize inner systems. Still others show potential habitable zones plagued by stellar instability. Within this diversity lies the puzzle. Habitable planets are not impossible, but they are outliers that demand rare alignments. Numbers help shape this perception, though with caution. Surveys suggest that small, rocky planets occur frequently, perhaps in half of Sun-like systems. But their potential for long-term habitability remains much lower once stellar activity and atmospheric retention are factored in. It is not that Earth-like planets are absent, but probabilities converge on the conclusion that they form a minority. Each advancement in spectroscopy reduced speculation, but increased awareness of these narrow windows. Among demonstrated milestones was Webb's 2025 atmospheric spectrum of WASP-39b, a hot gas giant, where CO2 and water vapor features stood clear. Though this specific planet is far from life-bearing, the measurement showed the method works. When scaled to smaller planets in the right orbits, the same techniques could define whether their skies contain water, carbon molecules, or other compounds relevant to life. Similarly, direct imaging of the HR 8799 system revealed massive young planets, serving as laboratories for atmospheric science. These observations grounded excitement in technical achievement rather than extrapolated claims. The impact of such results lies not in immediate confirmation of life, but in narrowing the field with evidence. They allow astronomers to dismiss many worlds quickly as hostile, while refining targets where further effort makes sense. Each transit spectrum gathered becomes a piece of a larger filter, and every filter confirms that most worlds fail at least one criterion essential for biology. The paradox grows sharper. Planets fill the galaxy, but the narrow trail leading to genuine habitability contracts with every dataset. Even so, the search is far from discouraging. In fact, the act of probing increasingly detailed atmospheres enhances the significance of the few candidates that remain. If a handful of exoplanets show the right signatures, then they become focal points for decades of study. The discipline no longer asks whether planets exist, but whether any of those planets carry the settings we rely on here. And in that shift, the improbability of Earth does not diminish, it intensifies. The cumulative impression is one of a universe that permits many worlds, but limits their suitability through tight rules. Discoveries of water vapor or carbon dioxide are essential for technique and for refining models, but no detection so far has proven hospitable settings across the long timelines needed for life. The year 2025 confirmed that hope must be tempered with caution. Finding water vapor is important. It is also a reminder that surface stability demands much more. This tension between abundance of planets and the scarcity of truly habitable ones mirrors the fine balances seen in cosmic constants and galaxy formation. Evidence accumulates, probabilities are revised, yet the central observation persists. Complex life requires rare alignments, and as astronomers reflect on those alignments, the question shifts from measurement alone to interpretation. Why do conditions look so accommodating in our case, but so restrained everywhere else? Finding water vapor is big, but it raises as many questions as it answers. The Anthropic puzzle. The search for habitable worlds raises a deeper issue not about planets but about perspective itself. This is the starting point of what is called the Anthropic principle. Its central claim is straightforward. We find a universe that looks suited for life, because only in such a universe could we ever exist to take notice. All other possibilities would remain unobserved, silent, and invisible. In this view, our presence shapes what kind of universe we are even able to describe. At first, this sounds like an elegant way to approach the fine-tuning puzzle. Scroll back through cosmic history and ask, why do the constants line up so precisely? The Anthropic reply is that we should not be surprised, because if they had been otherwise, observers would never have appeared to ask the question. What seems like design might be nothing more than a selection effect. Like water creatures always finding themselves surrounded by water, living beings inevitably describe a world consistent with their survival. But the simplicity of the idea can also feel unsatisfying. Telling ourselves that life exists because conditions supported it risks falling into circular reasoning. It explains the observation by restating it. Things look this way because if they did not, no one would be here to comment. Many critics argue that this does not resolve the central mystery of why the constants, forces, and balances took the values they did. Instead, it risks sounding tautological, an answer that closes the subject rather than opening it. Philosophers and physicists distinguish between two versions of the principle. The weak anthropic principle acts as a methodological reminder. Our observations are conditioned by the fact that we exist in life-supporting circumstances. It is not in itself an explanation, but a note of caution about bias. The strong anthropic principle goes further and suggests that the universe must, in some sense, be structured to produce life, or that observers are in some way necessary outcomes. This strong reading shifts from physics into philosophical interpretation. Many scientists are willing to accept the weaker form as a constraint on reasoning, while the stronger form sits uneasily in scientific discussions because it appears to invoke purpose or necessity without mechanism. One illustration often used in the literature makes the logic concrete: the firing squad analogy. Imagine a prisoner facing an execution by dozens of riflemen. Every shot is fired, yet the prisoner survives unharmed. Looking back, the prisoner wonders at the improbability. The anthropic principle would say, of course the survivor perceives the unlikely outcome, because had the shots not all missed, there would be no observer left to reflect on it. As with our universe, the fact of observation already filters the possibilities. This analogy clarifies the reasoning but also highlights the point of discomfort. Is survival a matter of luck, or is there an explanation we have missed? By 2025, theoretical debates had revisited this distinction with renewed focus. Some physicists argued that without a full picture of all possible universes, we cannot meaningfully assess how unlikely ours is. With only one universe in hand, probabilities become slippery. Under these conditions, the anthropic principle sidesteps the problem by arguing that statistical comparisons may not be meaningful at all. We measure only what is compatible with our existence, so the broader distribution might forever remain hidden. Others resisted this conclusion. They warned that relying too heavily on anthropic reasoning risks ending inquiry prematurely. If every surprising value is dismissed as a selection effect, science would no longer need to search for physical laws that actually produce those values. Yet history offers reminders that apparent coincidences sometimes hide deeper necessity. Planetary orbits once seemed arbitrary, but Newton's mechanics revealed predictive order. Similarly, today's constants may still have explanations waiting to be uncovered. For this reason, many researchers treat the anthropic principle as a constraint rather than a full explanation. It highlights bias in observation, but does not substitute for hard mechanisms. The anthropic puzzle also raises questions about objectivity. In most sciences, the observer can stand outside the system being studied. Here, the observer is entangled in the object of investigation. We exist because conditions permitted it, and this makes complete neutrality impossible. Universes that fail to produce life leave no witnesses, no data, no memory. Survivorship bias elevates our own case, making it appear unique without telling us whether it is exceptional or common. We cannot know how often life-permitting windows might arise in a hypothetical ensemble. This invisibility cloaks the failures and leaves us with skewed perception. Such filtering unsettles our expectations about purpose. Many interpret fine-tuning as intentional, reading meaning into the fact that constants sit so narrowly between extremes. The anthropic approach grants a more austere alternative. Perhaps no purpose exists. Instead, observers arise only in the rare niches where the physical framework allows survival. Any sense of cosmic preparation then vanishes, replaced by a logic of inevitability. We feel the outcome is special, but the uniqueness may be nothing more than the mathematics of selection. If no one could exist in uninhabitable worlds, of course we find ourselves in a habitable one. Even among those who adopt this line, consensus is scarce. Some accept the weak anthropic principle as a sober methodological tool. It keeps probability claims grounded in what can be known. Others find even that uncomfortable, concerned that it dilutes science's search for genuine mechanisms. Both sides acknowledge that the principle alone does not say why constants have the values they do. It reminds us that our viewpoint is biased, but whether the universe is fine-tuned by necessity, by chance, or by deeper laws remains unaddressed. This is why the anthropic puzzle endures. On one hand, it reframes fine-tuning as inevitable bias in observation. On the other, it leaves untouched the possibility that there might still be hidden physical reasons for the values we measure. Many scientists make the distinction explicit. Anthropic reasoning is a constraint, not a conclusion. It cannot stand alone as the ultimate explanation. What it does is remind us that the very act of observing conditions already selects for life-permitting outcomes, shaping which questions we get to ask in the first place. Seen this way, the anthropic principle does not close the fine-tuning debate, but reframes it. It shifts the puzzle from constants themselves toward the intersection of life, perception, and reality. Perhaps the constants are what they must be. Perhaps we read design into survival. Either way, our role as observers ensures that our account of the universe is inseparable from our existence within it. Whether we treat that as a methodological caution or as a profound philosophical challenge depends on the expectations we bring. And with that recognition, the question sharpens rather than fades. If anthropic reasoning shows only that we must observe a life-friendly world, then other possibilities open in response. Some argue that countless other universes might exist, each with different values, making ours merely one case among many. Others propose intentionality or design, suggesting purpose behind the balance. And still others ask whether our reality might not be fundamental at all, but a constructed or simulated environment. Each of these options attempts to address what the anthropic principle alone cannot. It is to these proposed responses, multiverse, design, and simulation, that the discussion must now turn. Multiverse, chance or design. One of the most widely discussed attempts to address fine-tuning turns to the possibility of the multiverse. Instead of one universe with one set of physical constants, the idea is that there might be countless universes, each with its own variations in the laws of physics. If that were the case, then the extraordinary precision we observe here would not require extraordinary explanation. Universes inhospitable to life would remain empty, while in rare instances where constants lined up correctly, galaxies, stars, and observers would emerge. On this view, our existence could be no great mystery. We simply occupy one branch where conditions happen to work. The appeal lies in how this perspective shifts the burden. Instead of asking why our universe looks so carefully calibrated, it proposes that every possible set of values exists across different universes. Given enough variety, even highly unlikely parameters would show up somewhere, and life would appear in those rare pockets. From this angle, what we call fine-tuning becomes statistical inevitability rather than intentional design. Yet it comes with an equally unsettling implication. If the multiverse exists, then our universe is not special. It is one in a vast multitude, and the fact that it allows life tells us only that we live in a domain where survival was possible. Contemporary physics has given some support to this possibility. Certain models of cosmic inflation, a theory describing how the universe expanded in the earliest fractions of a second, predict that inflation does not halt everywhere simultaneously. Instead, regions bubble off and stop inflating, while other regions continue the process indefinitely. Each bubble would then become its own universe, cut off from others by vast expanses of inflating space. This mechanism, known as eternal inflation, provides the framework for generating innumerable universes rather than a single one. At the same time, developments in string theory introduce the concept of a landscape of possible vacua, different low-energy states, each with its own values for physical constants. Combined, these two ideas form the technical roots of many multiverse proposals. Eternal inflation produces the bubbles, and the string landscape determines which constants each bubble inherits. Quantum theory also introduces a possible pathway to multiverse reasoning. The many worlds interpretation holds that every quantum event branches into multiple outcomes rather than collapsing into one result. Each branch represents a universe with its own history, growing side by side with all others. While debate continues over whether these branching worlds differ only in outcomes or also in their underlying constants, some physicists argue that the many worlds picture suggests a reality where all possibilities exist. Though this approach differs from inflationary models, both open the door to thinking that our finely tuned values may simply be one expression among an uncountable number of alternatives. By 2025, refinements in inflationary physics and explorations of string theory gave the multiverse a stronger theoretical spine than it had in earlier decades. What had once lingered on the margins of cosmology began to receive more mainstream discussion. Some inflation models and certain string theory landscapes predict a multiverse as a plausible outcome, and many cosmologists now treat it as a serious theoretical possibility, though it is important to note that it remains unproven and debated. Advocates highlight how naturally these frameworks generate ensembles of universes, while detractors stress how little contact such reasoning makes with observation. This limitation underscores the central weakness of multiverse claims. There is no direct evidence. The separate bubble universes created by eternal inflation would be permanently beyond reach. Branches from many worlds cannot be tested against ours. Observations in our universe cannot confirm the existence of counterparts outside it. Because science relies on testable predictions, critics argue that the multiverse risks crossing the line into philosophy rather than physics. Supporters respond that if theories already accepted for other reasons, such as inflation, point toward multiverses, it would be intellectually dishonest to ignore those implications simply because they are hard to test. Some propose that indirect hints might appear, for instance in polarization patterns of the cosmic microwave background, or in showing how a multiverse framework resolves problems other models cannot. Yet firm detection remains out of reach. Even if accepted, the multiverse raises philosophical complications. Consider probability. In an infinite ensemble of universes, every possible configuration not forbidden by logic or physics should occur somewhere. That means rare outcomes need no deeper explanation. They are guaranteed to appear countless times. Our life-friendly environment would be just one occurrence among infinitely many. But critics note that such broad reasoning risks committing what philosophers call the inverse gambler's fallacy, assuming that the mere fact of our fortunate observation is evidence for a large number of unseen trials. Just because we pulled this lucky ticket does not prove there were infinitely many draws before it. The debate over whether fine-tuning implies multiple universes, or whether that inference misuses probability, continues actively in philosophy and cosmology. Beyond probability, a second challenge confronts the multiverse framework. If every possibility occurs somewhere, then the concept seems to lose explanatory precision. An account that allows all outcomes risks predicting none in particular. If anything and everything can be said to exist across the ensemble, then our observations cannot verify or falsify the claim. Critics argue that, in this way, the multiverse may move the riddle outward rather than solving it. It explains the apparent fine-tuning only by appealing to roomier mathematics, without clarifying why inflation exists, why string landscapes contain such vacua, or why physical law permits universes at all. For others, this shift is less troubling. The multiverse operates not by providing a new design, but by rendering design unnecessary. In this picture, improbability is reframed. What astonishes us as fine-tuning is only the property of being inside a rare but inevitable situation. In a vastly large backdrop, accidents will occur, and life simply rides on one of those accidents. From this standpoint, the multiverse functions as a dilution mechanism, turning what appears extraordinary into something routine when viewed on a grander stage. Still, the approach leaves unanswered questions. If our universe is a bubble among many, why does inflation exist at all? If the string landscape contains countless potential vacua, why should it exist in that form? If many worlds are real, why does the quantum framework allow such branching? The multiverse can make life-friendly constants less surprising, but it does not dissolve the mystery of fundamental laws. It shifts the problem to a higher level without resolving what created the rules of the system itself. Some researchers accept that as progress, others see it as sidestepping the original puzzle. Support also varies in strength across the scientific community. Some physicists cautiously treat the multiverse as a serious speculative possibility linked to inflation and string theory. Others view it as a philosophical construct rather than a scientific hypothesis, precisely because of its resistance to direct test. Both sides acknowledge that it occupies an unusual space in science, arising from established ideas, but extended to boundaries science cannot currently pass. In summary, the multiverse can dissolve fine-tuning into chance, but because it is difficult, perhaps impossible, to test directly, it risks shifting the mystery rather than solving it. Instead of removing the sense of improbability, it reframes it into a discussion about unobservable domains. The question becomes not whether life-friendly universes exist. They would, in some of these models, but why the mechanisms capable of producing such universes exist in the first place. And yet, as debates over the multiverse demonstrate, when attempts to explain fine-tuning move beyond what can be observed, they blur the line between scientific theory and deeper speculation. In the years around 2025, that boundary began to shift even further, as unexpected developments in quantum experiments suggested strange new possibilities about the underlying fabric of reality. Quantum discoveries and the simulation question. In 2025, progress in quantum research accelerated and brought with it some of the most intriguing discussions about the nature of reality. New experiments refined how scientists studied entanglement and particle correlations, including work in Kyoto that demonstrated controlled measurements of multi-particle W states. Other initiatives, highlighted during the International Year of Quantum, showed advances in quantum communication and simulation technologies, strengthening our ability to work with systems that once seemed impossible to test directly. These breakthroughs pointed to new capacities in handling quantum information rather than to any hidden metaphysical truths. Still, for many observers, They stirred deeper questions about what quantum mechanics might imply about the structure of the universe itself. When entangled particles are measured, correlations emerge in ways that defy classical intuition. Results recorded across long distances align more precisely than chance would allow, underscoring that quantum systems behave not as a collection of independent parts, but as wholes linked by informational rules. In 2025, improved detectors allowed laboratories to perform such measurements with increasing sophistication. For physicists, this was proof that seemingly abstract quantum states could be prepared and studied at practical scales. For broader audiences, such patterns inspired comparisons to information systems, or even to the workings of computation. While data showed only correlations within physical laws, the language of information made the experiments easier to describe and provoked speculation that perhaps the universe behaves like a system processing information. To illustrate the idea, some drew analogies with computers. In digital systems, streams of ones and zeros create ordered patterns shaped by code. Likewise, in highly controlled experiments, quantum states arrange themselves with remarkable regularity rather than dissolving into apparent disorder. From a scientific standpoint, this reflects the mathematical constraints of the wave function and the rules of entanglement. To the more speculative imagination, it feels faintly reminiscent of engineered behavior. The resemblance led to renewed discussion of an old philosophical notion, the simulation hypothesis. The simulation hypothesis proposes that our universe might not exist as a base layer of reality, but as a constructed environment running on some substrate beyond our reach. In that framing, the fine-tuned constants of nature would not be statistical accidents, but choices made to ensure stability. A system designed to host complexity would be adjusted in just the ways we observe, much like programmers select parameters that keep digital simulations from crashing. By this logic, our physical laws could be interpreted as the output of code rather than eternal principles. Advocates point out that this scenario would provide a straightforward resolution to the fine-tuning puzzle. Instead of invoking improbable coincidence or an infinite ensemble of universes, the simulation view holds that the laws of physics look calibrated because they were calibrated. The peculiarities of quantum mechanics, non-local entanglement, probabilistic outcomes, unexpected correlations, could be seen not as physical confusion, but as evidence of hidden rules in an information processing environment. What appear random or discontinuous effects might simply be artifacts of working inside programmed constraints. But while the analogy is thought-provoking, most scientists remain cautious. They emphasize that none of the quantum results observed so far provide evidence for a simulation. Entanglement correlations follow equations set down in quantum theory. Measurement oddities are consistent with widely tested models of quantum mechanics. Experiments in 2025 demonstrated improved control of these systems, but they did not show glitches, hidden codes, or purposeful design. Scholars stress that the simulation hypothesis belongs not to physics but to philosophy. It cannot be tested with present methods, and without predictions that could be confirmed or denied, it lacks the markers of scientific hypothesis. This recognition draws the boundary clearly. Physics progresses when new experiments refine theories, constrain parameters, and generate reproducible results. The simulation idea, by contrast, remains unfalsifiable. Every observation fits within the simulation if we assume it does, but no observation can show that it must. For that reason, many researchers caution against conflating intriguing laboratory progress with evidence of design. At its strongest, the hypothesis serves as metaphor, an imaginative way to picture how information might underpin our universe. At its weakest, it risks halting inquiry by claiming intention where mechanisms remain undiscovered. Still, the thought persists because of the scale of the implications. If reality were simulated, then the constants of nature would have meaning not as natural givens but as settings on a system. The stars above, the the galaxies across space, even the particles in a detector would be representations within a larger structure. Natural law would lose its eternal aura and become simply consistent behavior within a programmed frame. For those inclined to explore such possibilities, quantum quirks become narrative hints, pointing not to physics alone but to hidden architecture. The unsettling part comes from imagining what such a simulation would entail. If engineered, it could be altered, paused, or ended by its operators. Existence would appear solid, yet depend on choices made outside it. That possibility carries weight beyond physics, influencing how some people think about permanence and purpose. Would life have inherent meaning, or would it exist only as long as some remote system sustained the simulation? Such questions remain firmly on philosophical ground, but the emotional force of the idea helps explain its endurance. In most laboratories, scientists focus on the measurable. They calculate predictions, test them against data, and refine models. The experimental progress of 2025 was celebrated less for speculation than for its tangible achievements, improving quantum error correction, demonstrating new entanglement protocols, and strengthening quantum communication. These advances have real technological futures in computing and secure information networks. Philosophy may draw metaphors from these results, but physics itself builds from them concrete paths of progress. Even so, the imagery cannot fully be contained. The parallels between information and physics encourage reflection on whether our perspective is narrower than reality itself. Perhaps quantum mechanics only look strange because we expect classical clarity. Perhaps the temptation to see code stems from the mind's reliance on patterns. Or perhaps, as the simulation hypothesis suggests, we really are encountering shadows of programmed behavior. None of these outcomes can yet be settled. The debate reflects a wider dynamic in cosmology and physics. When the universe appears improbably precise, discussions wander down speculative avenues, multiverses, anthropic principles, simulations. Each tries to account for striking balances without invoking coincidence. Yet science insists on evidence, and by that standard, only some frameworks remain secure. The simulation concept, though seductive, belongs on the speculative side, reminding us as much about human imagination as about the universe itself. Scientists stress this with clarity. None of the quantum discoveries to date provide evidence that our universe is a simulated system. They reveal strange, fascinating details about entanglement and quantum information, but those results fit within the framework of established physics. The simulation hypothesis remains an unfalsifiable possibility. It sits at the intersection of philosophy and culture, not at the center of experimental science. This distinction matters. Respecting the line between physics and speculation ensures that inquiry continues without mistaking imagery for proof. At the same time, keeping the question alive in imagination preserves perspective on how extraordinary the universe already appears. For audiences, that tension may be as instructive as any conclusion. The curiosity remains. If the cosmos feels engineered, is that just a product of our interpretation, or is there something deeper? For now, researchers set the question aside, focusing instead on what can be measured with precision. And that brings attention back to fundamental puzzles still rooted in data, the invisible matter and energy that dominate the universe but continue to elude direct detection. Dark matter and dark energy, the most perplexing ratios. In cosmology, the most confounding ingredients are not the stars and planets we see, but the invisible components that outweigh them. Dark matter and dark energy dominate the structure and fate of the universe, yet neither has been detected directly. Together, they account for about 95% of the cosmic energy budget, leaving ordinary matter, the atoms that make up stars, planets, and people, at only about 5%. Roughly 27% of the universe is dark matter, inferred from its gravitational effects, and around 68% is dark energy, driving cosmic acceleration. These ratios look convenient for supporting structure. Why they take these particular values remains one of the deepest puzzles in modern physics. Dark energy acts on the scale of the entire cosmos. Its effect is like a pervasive pressure, encouraging expansion rather than collapse. Observations show that this expansion has been accelerating for billions of years. If dark energy were even moderately larger, the acceleration would have been stronger, and matter would have drifted beyond reach before galaxies could form. If it were smaller, gravity would eventually have overcome outward motion, reversing expansion into collapse. Either extreme would leave no time for stars and planets to appear. The present value sits within a narrow zone where expansion continues, yet still allows structures to condense and endure. Dark matter works on a very different scale. It does not shine or absorb light, but it reveals itself through its gravitational pull. Rotation curves of galaxies show that stars orbit too rapidly to be held in place by visible matter alone. Gravitational lensing, the bending of light around massive clusters, likewise signals extra mass unseen by telescopes. Without this additional component, galaxies would not hold together or even form disks in the first place. But the role of dark matter is also sensitive to its amount. Increase it too much, and material would collapse into dense objects or black holes before stable galaxies could emerge. Reduce it too far, and the scattered atoms remaining would never clump into stars. Between these extremes lies only a small range where long-lived structures can develop. By 2025, measurements had sharpened estimates of these proportions and highlighted how tightly they constrain the cosmic setting. At approximately 27% dark matter, 68% dark energy, and 5% ordinary matter, the observed mix sustains galaxies for billions of years. Simulations show that even small shifts in this balance would radically alter outcomes, either preventing galaxies altogether or disrupting them long before stars completed their life cycles. The alignment is striking because dark matter and dark energy act on opposite scales, one binding galaxies together, the other stretching space itself. Yet both converge on values that permit long-term stability. Webb studies in 2025 added an indirect but important contribution. Imaging of early galaxy formation and luminous nebulae provided clearer timelines for when stars formed, dispersed elements, and regrouped into later generations. These observations tighten the models that simulate how ordinary matter interacts within dark matter halos under a background shaped by dark energy. The better researchers understood star formation, the more precisely they could determine how much scaffolding dark matter must provide and how much pressure dark energy must apply. The Webb data did not measure those components directly, but it narrowed the ranges consistent with what the telescope recorded. What makes this situation more puzzling is how fragile the balance looks. Dark matter holds galaxies together against internal dispersal, while dark energy pushes outward to prevent large-scale collapse. If their relative strength shifted by even modest amounts, one side would overwhelm the other. Galaxies might never appear, or they would rapidly disintegrate. The fact that these values land in a mutually supportive zone has led scientists to call it the coincidence problem. Why should two unrelated, invisible components exist in precisely the proportions that permit life-sustaining structures? Some findings in 2025 emphasized the narrowness of this balance even further. Earlier cosmological models had allowed more flexibility in dark energy's value over cosmic time, but refined surveys of distant supernovae and background radiation suggested stability within very small tolerances. For dark matter, mapping gravitational lensing events and comparing them with simulations produced tighter bounds on clustering. Once again, the conditions that allow galaxies to maintain stars across billions of years turned out to be perched on slimmer margins than expected. These results left open the same uneasy question that shadows fine-tuning in general. Many physical constants can be measured directly, like the charge of the electron. Dark matter and dark energy, in contrast, appear only through indirect effects. They form the unseen scaffolding on which visible reality rests. If their values were different, the universe would display neither familiar galaxies nor the chemical environments needed for life. At the same time, nothing in theory yet explains why these numbers are what they are. The appearance is one of convenience, but whether that signals design, deeper physics, or chance remains unresolved. Some researchers argue that the problem may eventually dissolve with new theory. Perhaps a unified model will reveal why dark matter density settled at its present value and why dark energy behaves as it does. Others suggest the coincidence could be an artifact of our perspective. We live during an era when both components are comparable in strength, because only then are observers possible. In the far future, when dark energy dominates completely, galaxies may vanish from view. In the distant past, before expansion accelerated, structures were just beginning. Our awareness may fall precisely at the intersection that favors measurement. Whatever the explanation, the role of these ratios is fundamental. They regulate not just galaxies, but the entire timeline of stellar evolution. With slightly different proportions, stars might form too quickly and burn out before dispersing elements like carbon, or form too slowly to generate planets in time. The measured balance ensures a cycle of creation, destruction, and renewal that has unfolded over billions of years. Every heavy atom in human bodies was forged in that cycle, made possible by invisible ratios that no one fully understands. The more astronomers refine the numbers, the clearer the puzzle becomes. Dark matter and dark energy remain hidden, yet their combined effects are written across every image of deep space. Galaxies that persist instead of dissolving, clusters that bend light, supernovae that trace expansion. Data confirm their presence with growing precision, but not their identity. Behind all the measurable phenomena lies the mystery of why their fractions align as they do. Instead of treating them as symbols of design or calibration, many physicists take a more neutral stance. Their proportions simply look convenient for structure, and understanding why remains an open challenge. This framing preserves the puzzle without assuming intention. It leaves room for new theories, perhaps in quantum gravity or unification frameworks, that might one day reveal why the dark sector behaves this way. Until then, the coincidence problem holds its place as one of the most stubborn riddles in cosmology. And that leads to a further question that unsettles the conversation. If invisible components set the stage for everything we see, what set their values? Could laws of nature have shifted over time? What if the rules of physics we take as fixed were not constant after all? The idea that forces or constants might drift over time challenges the very foundation of stability in the cosmos. Life as we know it assumes unchanging conditions. Gravity that holds planets in orbit, electromagnetic forces that bind atoms, nuclear interactions that forge elements in stars. If those numbers shifted significantly, stars might never ignite, chemistry could unravel, and galaxies might collapse long before life emerged. For decades, physicists and philosophers have asked whether this bedrock assumption, that nature's constants are truly immutable, can be trusted. By 2025, technical advances allowed scientists to scrutinize the question with unprecedented precision. Their strategy was to treat the universe itself as a laboratory clock running for billions of years. The light of distant quasars offered a natural probe. These luminous galaxies, powered by supermassive black holes, shine across cosmic time. As their light travels through intergalactic gas clouds, atoms in those clouds absorb parts of the spectrum, encoding signatures of fundamental constants such as the fine structure constant, which governs how light and matter interact. When this ancient light reaches Earth, scientists can compare its spectral lines with those measured in present-day laboratories. Any consistent difference would hint at a shift in physical constants. The method is simple to describe but technically demanding. Match faint, redshifted absorption lines with laboratory precision and test whether nature's handwriting has changed across billions of years. So far, the majority of rigorous studies report no consistent, reproducible drift. The cosmic microwave background provides an even older check. This faint radiation, still visible today, was released when the universe was about 380,000 years old and atoms first formed. Its detailed spectrum contains information about how quickly matter and radiation behaved relative to one another at that time. Variations in parameters like the fine structure constant or the proton-to-electron mass ratio would have left identifiable imprints in that radiation. Thanks to refined satellite data and ground-based telescopes, measurements in 2025 could compare these ancient conditions with present rules. Again, they showed remarkable consistency. The forces and constants then and now appear practically identical within current limits of sensitivity. The implications of variation, even if minute, would be enormous. Imagine, for instance, that the fine structure constant had been slightly larger in the early universe. Hydrogen and helium atoms would have behaved differently, potentially preventing the cooling of gas clouds and delaying the birth of stars. If gravity's strength had shifted subtly, galaxies themselves might have failed to cohere, or they could have collapsed too quickly for planetary systems to stabilize. Stability across billions of years is essential not only for cosmic architecture, but also for life's evolution, which depends on consistent chemistry, steady starlight, and planetary environments that change slowly enough for biology to adapt. The data available by 2025 painted a striking conclusion. Despite sensitive measurements across time and space, no convincing evidence suggested major drift. Quasar absorption studies showed that the patterns of ancient atoms closely match those we observe now. Analyses of the cosmic microwave background revealed no large discrepancies either. The gravitational rules sculpting galaxies today appear the same as those directing the first stars. The nuclear forces binding protons and neutrons remain aligned with those inferred from primordial element formation. If there has been change at all, it is far smaller than would have altered cosmic history. Still, controversy lingers in a narrow margin. A handful of studies have reported hints of possible variations in the fine structure constant over very long distances or timescales. These claims include suggestions that alpha, the dimensionless measure of electromagnetic strength, may have differed subtly in opposite directions across the sky. Such papers attracted attention because they proposed a universe where constants might drift slightly depending on location or epoch. Yet follow-up analyses often failed to reproduce the effect, and critics pointed to potential systematic errors in observations. To date, no consensus supports these claims. Most physicists regard them as unresolved anomalies, not established results. The prevailing view is that if variations exist at all, they must be vanishingly small, far too slight to alter the structure of stars, galaxies, or chemistry. The lack of measurable change itself has consequences for how we think about fine-tuning. If constants could shift naturally, perhaps they might have wandered into life-permitting ranges over time, allowing biology to arise by gradual chance. But the evidence indicates otherwise. The values that allow for life were present from the earliest moments and have remained locked in place with extraordinary persistence. The universe's constants appear frozen across time, not adjusted, not corrected, and not softened by flexibility. This rigidity narrows the possibilities. The settings we observe had to be right from the outset and have endured that way ever since. For cosmology, this finding closes off certain explanatory paths. Hypotheses invoking gradual drift to reach special conditions cannot be sustained, at least not at scales that matter for galaxies and life. Instead, the entire cosmic narrative unfolds under fixed parameters, as if the rules were baked in with the Big Bang itself. Matter, radiation, gravity, and electromagnetism have unfolded their story without fundamental revision. This makes the question of origin more pressing. Why did the first moment of the universe already contain the exact values needed for long-term stability? Why has no variation crept in to alter them? The durability of these numbers turns the fine-tuning puzzle from one about probability to one about permanence. Stability also frames expectations for the far future. If constants have remained steady across more than 13 billion years, the reasonable forecast is that they will remain stable across trillions to come. Stars will live out their predicted lifetimes, galaxies will evolve according to known dynamics, and planetary orbits will not unravel because of shifting gravitational strength. Even the expansion of the universe is expected to follow the course implied by today's constants, not by drifting values. From one perspective, this reliability is reassuring. The cosmos is trustworthy at a fundamental level. From another, it is unsettling because it leaves unanswered why such trustworthiness exists at all. The possibility of mutable laws feeds speculation about parallel histories, universes that could have unfolded differently if constants had shifted. But the strongest message from 2025's evidence is that variation is at best negligible. The constants of nature seem to have been pinned from the start, producing a cosmos where stars, chemistry, and life could follow without interruption. This strengthens the weight of fine-tuning arguments by denying the easy escape of change over time. The odds of life permitting conditions being reached by drift collapse to zero, leaving the focus on how improbable initial conditions came to be. From the first atoms captured in quasar spectra to the faint glow of background radiation, the record looks consistent. The fine structure constant is steady. The mass ratio of proton to electron is steady. Gravity has not loosened or tightened its grip. Other constants tested reveal the same pattern. The universe does not appear to experiment with its own rules. Precision values were set, and endurance sealed them. A few voices keep open the debate, pointing out that no measurement is infinitely precise. Detecting tiny fluctuations requires pushing technological limits, and absolute certainty is unreachable. Ongoing research will refine tests with atomic clocks, interstellar observations, and next-generation telescopes. But even with this caveat, the evidence so far supports one takeaway. Any shift is either non-existent or too small to matter. That means life's possibility was not the result of flexible adjustment. It relied on constants being correct from the start and holding fast ever since. So far, constants look very stable, which makes the improbability of their precise life-friendly values more stark. They seem not to have drifted into the right zone. They were already there, and they stayed there. This outcome sharpens the puzzle, rather than dissolving it. And it raises a provocative question for what follows. If the constants have proven so unyielding, could it be that fine-tuning was never about luck or coincidence in the first place? Perhaps the universe did not stumble into balance at all, but unfolded according to deeper necessities we have yet to uncover. What if the universe was never lucky at all? Another way to approach fine-tuning asks whether luck was ever part of the picture at all. When scientists and philosophers have listed possible explanations for the universe's striking precision, three broad categories have dominated. Some invoke chance. In a multiverse of countless variations, at least one universe would eventually fall within life-friendly ranges, and ours is simply that one. Others interpret design. Constants appear set deliberately, suggesting purposeful calibration by some form of agency. But there is also a third possibility, necessity. This view suggests that physical laws and constants could never have turned out differently, because they arise from deeper mathematical or logical structures that leave no room for variation in the first place. The appeal of this inevitability perspective lies in reframing the entire puzzle. If constants could have drifted freely, their exact life-permitting values would appear staggeringly unlikely. But if variation was never an option, then the apparent improbability dissolves. In that case, the conditions we see are not surprising but unavoidable. no more accidental than pi emerging from the ratio of a circle's circumference to its diameter. Some theoretical work in 2025 pressed this direction, exploring whether constants could emerge from hidden symmetries or from deeper mathematical frameworks that enforce particular outcomes. Advocates argued that what appears finely balanced may in fact be rigidly constrained. The universe would follow its single permitted path, not because of chance or design, but because no other path is possible. Yet adopting inevitability is as challenging as it is intriguing. Scientific caution is warranted. Declaring constants forced by mathematics assumes a final theory capable of showing why they take their present values, and such a theory does not yet exist. We still lack a complete unification of quantum mechanics with relativity, and the origins of dark energy remain unsolved. Without a fully worked-out framework, necessity remains speculative. At best, it is a philosophical position shaped by hints from symmetry and mathematical consistency, but not yet demonstrable physics. Critics caution that it risks dismissing the real improbabilities too soon, treating unexplained precision as inevitable when we do not yet know enough to be certain. Philosophical debates surrounding this issue have been lively and rigorous. Some have formalized arguments that apparent fine-tuning supports some version of design, pointing to the improbability of constants falling within such a narrow band. Others, skeptical of the multiverse, highlight the risk of reasoning errors like the inverse gambler's fallacy, confusing our fortunate observation with proof of countless unseen trials. The necessity option sits alongside these, offering a sharp contrast. Its strength lies in cutting away both chance and external design, but its weakness is that it leaves unexplained why necessity itself takes the form we observe. Why these equations, these symmetries, and not others? Even if deeper mathematics locks the constants into place, we are left asking why reality corresponds to that specific mathematics. Each of the three approaches carries both promise and limitation. Chance through a multiverse makes life-friendly results seem ordinary, but it stretches the scientific method to domains we may never observe. Design or purpose resonates with the impression of calibration, but pushes the conversation into philosophical or theological territory beyond empirical science. Necessity promises clarity, making fine-tuning dissolve into inevitability, but requires a final theory we do not yet possess and leaves the origin of that necessity unexplained. None of these positions has emerged triumphant. Each addresses some parts of the puzzle while leaving others untouched. For viewers, what matters is less the immediate answer and more the recognition of where science stands. Every observation confirms precision, but no single explanation has settled the matter. Some scientists lean toward multiverse frameworks, others toward philosophical readings of design, and some toward the inevitability of mathematics. The debates are serious, ongoing, and engaged with both physics and philosophy. Not casual guesswork, but structured attempts to wrestle with one of the most difficult questions modern thought confronts. So the central choice remains open. Was life a matter of extraordinary odds, a consequence of deliberate adjustment, or the guaranteed outcome of laws that had no freedom to be otherwise? Each interpretation reshapes how we think about the cosmos, yet no experiment so far selects one path as conclusive. We stand at an intersection where data outline the improbability, but theory has yet to close the gap. Which of these three paths, chance, necessity, or design, feels most convincing to you? Tell us in the comments. Your perspective adds to a discussion still unfolding across science and philosophy alike. And as the possibilities remain unsettled, the question only deepens. Whatever the explanation, the universe still presents itself with a precision that seems impossible to ignore. In drawing the threads together, the discussion comes back to what remains undeniable. The universe works within parameters that seem improbably narrow yet consistent. Every constant and ratio we can measure supports the existence of galaxies, stars, and eventually life. Yet the main explanations on offer, multiverse chance, intentional design, or mathematical necessity, all leave us with unresolved questions. Perhaps the deeper issue is not how precision appeared, but why the universe's values let complexity exist at all. Science keeps sharpening the puzzle. The universe is precise, and the explanations all leave open deeper mystery. If you're fascinated, comment which explanation you find most convincing, and subscribe if you want updates as Webb and quantum labs push the question further.